Good evening, everyone. My name is Dr. Melanie Brickman-Borchard, and I'm Director of Life Sciences here at the New York Academy of Sciences. It's my great pleasure to welcome everyone here today in person as well as via live stream for our event, The Mystery of Our Mathematical Universe, the first lecture in our three-part series, Conversations on the Nature of Reality. This lecture is co-presented by the Noor Foundation, Wisconsin Public Radio's program To the Best of Our Knowledge, and the New York Academy of Sciences. I would especially like to thank Richard Rass from the Noor Foundation and Steve Paulson from To the Best of Our Knowledge for their incredible efforts in putting this series together. I'm pleased to say that this is the Academy's 8th series partnering with the Noor Foundation and 7th series partnering with To the Best of Our Knowledge. These events follow in the footsteps of series such as The Will to Meaning, Seeking the Why of Our Existence, From Knowledge to Wisdom, Science and the Good Life, and Unlocking the Unconscious, Exploring the Undiscovered Self. And you can revisit all of these series on both the Academy's website as well as the Noor Foundation's website. If you're not familiar with the New York Academy of Sciences, we're among the oldest scientific organizations in the United States, and we started just a few blocks away, right here in downtown Manhattan. In the past 200 years, we've grown from a small community of physicians and naturalists to a global organization of more than 20,000 members in 100 countries. In that time, the Academy has brought together communities from multiple sectors at conferences and events like the one today. They're designed to address pressing global challenges and build a bridge between scientists and the public. For those of you who wish to relive today's experience, you'll find this lecture online via the Academy's Livestream channel and in the coming weeks on both the Noor Foundation's website as well as their YouTube channel. For those of you who have attended our evening program before, you may notice a little different look to our stage. We have boom mics so that we can record this evening's conversation for potential use on the nationally syndicated Peabody Award-winning radio show To the Best of Our Knowledge, where interviews help fuel deep insights into our world. We thank all of you for being a part of this experience. And after our event, I hope you will all join us in the lobby for a reception. Now, before we get to stretching our minds as we think about what mathematics can reveal about the mystery of our universe, I'd like to ask you all to keep our space quiet and please silence your cell phones. Thank you all again. And now I'm happy to turn the stage over to Lisa Hauptman from the Noor Foundation, our presenting partner.
Thank you, Dr. Brickman-Steins. And on behalf of the Noor Foundation, we would like to thank the New York Academy of Sciences for hosting and partnering with us on this outstanding series. As you heard, this is the 8th consecutive season that the Noor Foundation has partnered with the Academy and To the Best of Our Knowledge to present timely and captivating discussions. We would also like to thank our distinguished speakers for being here with us tonight. For those of you who may not yet be familiar with the Noor Foundation, we are a public, charitable, and non-governmental organization in special consultative status to the United Nations Economic and Social Council. The Foundation's primary mission is to explore expressions of meaning and commonality in human experience, with the goal of engendering a greater spirit of unity, tolerance, and understanding. From its inception, the Noor Foundation has been inspired by the work of the late Ostarallahi, an influential thinker, jurist, and musician who devoted his life to the pursuit of self-knowledge and existential meaning. The Noor Foundation's multidisciplinary activities, which include topics on both the sciences and the humanities, highlight the value of contemplating questions of meaning and purpose objectively in today's modern world. The pursuit of these existential questions and the answers we provide not only inform our perspective and shape our convictions, but also frame our intentions, decisions, and actions in daily life. One of the central goals of the Noor Foundation is to stimulate informed discourse on existential questions from an objective and interdisciplinary perspective that is rooted not only in sound theories, but in the shared commonality of our personal experience as well. Our present series, Conversations on the Nature of Reality, we'll explore the fascinating relationship between our subjective experience, what we perceive through our senses, and the physical world surrounding us. Our first panel discussion tonight, The Mystery of Our Mathematical Universe, will seek to examine why it is that fundamental laws discovered through pure mathematics have been able to describe the behavior of our physical world with such remarkable precision. Because the physical world is comprised of mathematical properties, some believe that mathematics is the language of the universe, whose laws reveal what appears to be a hidden order in the natural world. Tonight, physicist Jim Gates and science writer Margaret Wertheim will discuss the uncanny ability of mathematics to reveal the laws of nature. It is now my pleasure to briefly introduce Wisconsin Public Radio's Steve Paulson, executive producer of the Peabody Award-winning public radio program To the Best of Our Knowledge, who will moderate tonight's discussion. Steve has written for Salon, Nautilus, Slate, The Huffington Post, and many other publications. His radio reports have also been broadcast on NPR's Morning Edition and All Things Considered. And his book, Atoms in Eden, Conversations on Religion and Science, has been published by Oxford University Press. Please help me welcome Steve Paulson and our distinguished panelists.
Well, thank you. I am thrilled to be here. What a great crowd. This is very exciting to see all of you here. If you have come to any of our previous series, you know that we like talking about the really big questions, the ones that extend beyond science and delve into philosophy and the search for meaning, and it doesn't get any bigger than the nature of reality. So we'll see how we do this evening. Now, it turns out that physicists in particular are obsessed with this subject. Now, I'm not a scientist, but I collect books about physics, and as I was preparing for this panel, I glanced over at the titles on my shelf, like The Road to Reality, The Hidden Reality, Quantum Reality, The Fabric of Reality, Decoding Reality. Reality is not what it seems. What is real? And my personal favorite, Farewell to Reality. So the question is, do physicists actually understand the nature of reality? I mean, are the laws of physics ultimately the deepest reality there is? Does it all come down to equations and mathematical formulas? Or is this obsession with mathematics or some kind of underlying Platonic order itself a kind of fool's errand? These are questions that we'll be looking at this evening. As I was preparing for this discussion, I came across a couple of quotes that I really liked. One is from Einstein: "Reality is merely an illusion, albeit a very persistent one." And the second one is from someone who is most definitely not a scientist, the gonzo journalist Hunter S. Thompson, who said, "I learned a long time ago that reality was much weirder than anyone's imagination." So we're going to talk about the weirdness of reality, the beauty embedded in the laws of nature, and much more. And lucky for us, we have two very smart people here who are going to help us figure it all out. So let me introduce them. S. James Gates, Jr. is a professor of physics at Brown University. He was previously at the University of Maryland for several decades. He's known for his work on supersymmetry, supergravity, and superstring theory. Professor Gates received the National Medal of Science for his contribution to science and research in 2015 and has served on the U.S. President's Council of Advisors on Science and Technology. In 2018, he was elected to the presidential line of the American Physical Society, for which he will serve as vice president and later president. He's the co-author of Superspace, 1001 Lessons in Supersymmetry and Reality in the Shadows, or What the Heck's the Higgs? He's co-authored more than 200 research papers and has also been featured in dozens of documentaries. Margaret Wertheim is a science writer, curator, and artist whose work focuses on relations between physics and the wider cultural landscape. She's the author of 6 books, including Pythagoras' Trousers, A History of Physics and Religion, The Pearly Gates of Cyberspace, A History of Scientific Concepts of Space, and Physics on the Fringe, a groundbreaking exploration of outsider science. She's an op-ed contributor to the Los Angeles Times, and she's written for the New York Times, New Scientist, The Guardian, many other publications. She is the co-founder and director of the Institute for Figuring an organization that promotes public understanding of the poetic and aesthetic dimensions of science and mathematics. Welcome, both of you.
Thank you,
Thank
Steve.
you.
Now, I know each of you has a deep affinity for mathematics. It seems to be personal for you, and I want to sort of dig into that. So, Jim, let me start with you. Why is mathematics such an interesting way to see the world?
Well, for those of us who are engaged in scientific and technical endeavors, it appears that among all the languages that humans have ever developed, this is the only one that is sufficient to the task of describing what you call reality. And I want to return to the reality part, because for a scientist, when we talk about reality, we mean taking our experience of observing and then asking, are there things out there that do not depend on our emotional state? That's how, I think that's the most fundamental definition of objective reality that a scientist
You want to
can give you.
divorce it from the personal.
It's like going into people's homes and asking, how does the house work when they're not at home? That's what science is all about.
Margaret, let me turn to you. Why mathematics? Why are you so obsessed with mathematics?
Well, Werner Herzog has something very interesting to say that I think is pertinent here. And I know Werner quite well, and he likes to say there are two kinds of truth. There's the accountant's truth, and there's the ecstatic truth. Werner, of course, is on the side of the ecstatic truth. And I think mathematics is on the side of the ecstatic truth. I think that most people think mathematics of being a kind of accountant's truth. And certainly historically there has been a lot of affiliations between mathematics and accountancy. But particularly modern mathematics is really, I think, an ecstatic exercise. It's like some sort of brilliant dream. And the way that I like to think about it is that I think of mathematics as being the language of pattern and form. So wherever you find pattern or form, there will probably be mathematical structure embedded in it. And since I've always been obsessed with pattern, I think that mathematics is just the natural and wonderful way of, in some sense, getting to the essence of what pattern is.
So I'm curious about how far this goes back for each of you, your fascination with mathematics. Jim, can you remember back to your childhood, and was there a moment when it suddenly hit you, this stuff is really interesting?
Well, in my case, it actually goes back to before I was born. Because it turns out that my grandfather could neither read nor write, but he could do arithmetic. And my father never finished high school, but I remember as a child watching him study trigonometry and some calculus. Mathematics is kind of the family business for me and my family and my kids. I have two twins that are STEM people, and it's all about mathematics with them too. I have nieces and nephews. But the time when it sort of personally dawned on me that mathematics was something rather extraordinary was when I was 15. When I was 4, I decided I was going to be a scientist. So I'm 11 years into this process by the time I'm 15 years old. And one day, my physics teacher performed an experiment. And the thing that you have to understand is, for me, mathematics was always an element of my imagination. It was like reading science fiction or going to the movies or fantastical stories. To me, mathematics existed inside of my head, and I was peculiarly aware of that. But one day in a physics class, my physics teacher showed me an experiment, a very simple experiment. You just roll a ball down an inclined plane, you measure the distance versus the time, and you can write an equation which describes that. And to me, I tell people that's the closest and only thing I have seen in life that looks like magic. It's like we're all at Hogwarts, right? You learn to conjure. The conjuring is with the tools of mathematics, not with the tools of Latin, as you would see in a Harry Potter movie. And so this actually burst upon my consciousness, 15 or 16 years old, and I've never recovered.
So did you feel like that moment in the classroom that sort of math was able to describe reality there?
No. What I understood about mathematics was that an element of my imagination apparently was accurately describing a part of what I considered outside of my head. And I'd like to return to this reality debate later so we can get into it, because let me do it now, in fact. There's a subtle thing about reality that I'm not sure we normally take into account. As was mentioned in the introduction, we know about reality through our senses. We build instrumentation, which are extensions of our senses. But the part of it that we can never get out of is the fact that we have a subconscious, an unconscious mind. They're kind of we're duality. Each one of us is sort of two beings. There's the rational being, and there's the unconscious, irrational being. And even for scientists, as we observe reality, that silent partner is in there. Sometimes it generates false data. And so when you talk about the power of mathematics, to me, it's the discussion between me, the rational me, the universe, and the subconscious irrational me, over which I have no control whatsoever. And out of that cacophony, there's this one language that seems to allow us all to have the conversation.
So, Margaret, I'm wondering how much this resonates with you, and going back to your childhood, was math a part of your imagination?
I was very lucky in that in primary school I had a couple of teachers who were very, very good math teachers. And I just went to a really third-rate public school in the outer suburbs of a country town in Australia. So it wasn't any fancy school. But I had one particular math teacher, Mr. Marshall, in grade 5, and we should all give a shout out here to the amazing math teachers who are so much a part of the necessity of raising scientists. And when I was in grade 5, Mr. Marshall gave us a lesson about circles. And instead of just telling us about pi and saying, the circumference of a circle is 2 pi r, he had us drawing circles on graph paper and measuring the diameter versus the circumference. And the idea was that we were to discover pi for ourselves. And he sent us home and said, you go away and sort of think about this. And I spent the night drawing circles on graph paper, and I realized there was this very special number. And it wasn't like 2 or 3 or 4. It was some very special number that determined this relationship. And I had this sort of blinding revelation. I remember that literally the world lit up, and it was like, oh my God, there's this thing called pi, and it's in the heart of every time I see a circle, in the hubcap of a car, in the pearls my mother wore, in the shape of the sun and the moon. And there was this magical number there. And I think ever since then I've been obsessed with what is the meaning of the mathematical relationships that we find in nature. But I think what's critical about this is that I was allowed to discover a mathematical thing for myself. Of course, I wasn't the first person in the history of the world who's discovered pi. Millions of people have. But I made a mathematical discovery for me, and math therefore came alive.
So I'm fascinated by this because I do not think in mathematics like either of you do. And so I'm sort of trying to put myself into your minds in some way. So what does that mean to think mathematically? I mean, do you think about different kinds of things? Do you sort of order the world in a different way? Jim?
Well, it's a little bit like you're asking me to imagine the world. How would I see the world if I was blind? I can't do that. For people like me, mathematics is intimately part of who we are, even down to the emotional level. It's not just an engagement at the rational level where it's a useful tool for balancing checkbooks, say, right? But when you engage math at this level, what you find is it is as beautiful as any form of art that humanity has ever constructed. In fact, I think, now I'm waiting to hear Margaret, but for me, it is indistinguishable from art at some level. But it has this other useful property. It allows me to build apps. And it's the only form of art that I know that does that.
Well, we were just talking before we came out on stage here, and you said that you have math dreams.
Yeah, I dream in math sometime. But I'm not the only one.
What kinds of dreams?
Well, the ones that are useful, because there are lots of ones that aren't useful, but the ones that are useful are actually the ones that help me solve my rational mind's puzzles in equations that have to do something with string theory. But yeah, there are dreams that are connected to that.
Wait, I'm just trying to get a sense of this. So
Yeah.
you wake up, you remember your dream, and this will help me in this project that I have?
Yes. I know it sounds like magic, and it sounds like the things you read about, but if I was writing a novel or a poem, none of you probably would say, oh, it's extraordinary that he has a muse that speaks to him when he awakens and allows him to create this beautiful verse or to tell this daring story. Humans are very well accommodating of the notion that creativity in the arts comes from this sort of mysterious place. But I think for people like us, it seems like it's the same place. It just expresses itself in a different way.
Margaret, do you have math dreams?
I don't have math dreams, but when I should say I'm not a professional mathematician, unlike Jim. I went to university and studied physics and math for 6 years and originally thought I would be a theoretical physicist. But when I was at university, it would definitely happen numbers of times that you'd be set a problem and you'd come back next week with the answer and you'd be thinking about it. And then after days of this, you would wake up, literally the answer had come to you while you were asleep and dreaming. And I think all scientists have this phenomena and mathematicians. And so that does kind of make you wonder where does it come from? But there's a quote by a 19th century mathematician that I really like that sort of gets at something about this. His name was William Playfair, and he was one of the mathematicians who was involved in the modern understanding of what's called hyperbolic geometry. And he lived at the time when mathematicians were discovering things like Mobius strips and Klein bottles and infinite dimensional mathematical spaces. And he said this great quote, he said, "We become aware sometimes how much further reason may sometimes go than the imagination may dare to follow." And, what he was saying is that, reason had led us to think supposedly impossible things like the Mobius strip and infinite dimensional spaces, which are mathematically easy to write down, but sort of almost impossible to imagine. And so it seems to me that, there is this sense in which mathematics is a dream. And in fact, when we were preparing for this event, I think one of the original points of inspiration was Eugene Wigner's famous paper about the unreasonable effectiveness of mathematics in the material world. And I reread the paper in preparation for this. And what's so astonishing about it is he keeps on insisting that mathematics is made up. And that's his term.
Well, there's this age-old debate. Is mathematics discovered or is it invented? So which is it?
So
I want to hear Jim's answer.
So remember, well, first of all, thank you for the accolade of calling me a mathematician. I have many mathematician friends who would be insulted by that. I am a theoretical physicist, not a mathematician, and they make sure I keep that in mind almost every day. Physicists believe in quantum mechanics, so you asked me for one answer, so I'm going to give you two. When you are in the struggle to solve a mathematical problem of some significance, it feels like you build it piece after piece after piece. So it feels like you are making it up. But after you have the answer, it feels like it was always there waiting for you to find it. So that's my answer. It's both to me. I've experienced both.
Well, I think I've been obsessed with this question for as long as I've been conscious, or since as long as I've been conscious of mathematics. And, Leopold Kronecker, the 19th century mathematician, said, God made the integers, the rest is the work of man. But there's a contemporary mathematician and philosopher of mathematics, Brian Rotman, who's written this wonderful book called Ad Infinitum, Taking God Out of Mathematics and Putting the Body Back In. It's a book about it's trying to come at a non-Platonist account of mathematics. So try to come to an account of mathematics where we don't see it as something above and beyond the material world. And I'm completely convinced by Brian's argument. And what he says is, he said, even the integers are the work of man. And he claims, and I fall on this side, that I think mathematics is, as it were, made up. That doesn't mean that it's not true in some sense, but I don't think there's a sense in which mathematics has an existence above and beyond conscious beings who can, as it were, think it.
So the sort of one of the questions we're trying to get at here is mathematics, these elegant formulas. Is that ultimate reality? Is that sort of as deep as it goes? And Jim, I sort of get the sense that you think, yes, that is the deepest kind of reality.
No.
No. Okay.
And I'm not being a contrarian, but literally no. So, as someone, I'll soon be 68 years old, and so, I've had a couple of decades of thinking and working in this area. And what I've concluded is the following, that it's not necessarily the case that mathematics is the ultimate expression of reality. It may be the case that it is the ultimate expression of reality that humans can understand. And there's a subtle difference between those two things. It comes back to this comment I made to you earlier. I don't know as a rational being how I free myself from my subconscious. And therefore, it molds my thinking. In fact, there are people who will conclude that the rational mind is actually a construct of the irrational mind, that we post-explain how we come to decisions, that in fact it's a completely irrational, emotional process of work, and then we make up an excuse, and so, yes, I figured that out. Now, I don't know that that's exactly true, but that to me is not, there's an element that I feel that as we think about how, and I'm glad Margaret used the word conscious as opposed to human, because I think that's a key to it, that it's a conscious, rational being that I think would come independent of what planet, I'm a science fiction fan, so we believe in all that stuff out there, but I believe that any rational being observing the universe will be driven to a mathematics that will be universally recognizable. But as to whether mathematics is reality itself, that's a bridge too far for me to take.
Okay, so if there are rational beings on another planet with an entirely different evolutionary history, will they discover the same mathematics that we have here?
They'll know about pi.
There's an aesthetic dimension to all of these questions as well, and a lot of people have talked about the beauty of math, the beauty of the laws of nature, and I'm wondering how far we can take that. And I particularly am interested in your take, Margaret, because you work in art.
Yes, I do some projects at the intersection of mathematics and art. So personally, I find mathematics extremely beautiful. But beauty is a very multivalent concept, and at least when we talk about mathematics in the world, which a lot of physicists talk about, they seem to automatically now equate the concept of beauty with symmetry. And there's an awful lot of mathematics aimed at finding what's called the symmetries between things, and symmetries become a kind of obsession, a beautiful obsession by modern physics and mathematics. But, I do my art projects with my twin sister, who, when we left school, after high school, I went to university and studied physics and math. She went to art school. And sometimes she's really into math and science, but sometimes I show her things that I think are really beautiful, that are really, incredibly supersymmetric things about mathematics. And she just looks at it and says, that's boring. Because coming from the aesthetic world, she teaches, art students about aesthetics. And in the contemporary art world, symmetry is not affiliated with beauty. It's just seen as boring. And so the notion that beauty is universal, which is something that keeps being uttered in physics books, is just nonsense. There's an amazing show on that you should all go and see right now at Pioneer Works, that is a show of Haitian art inspired by voodoo. I think it's the most drop-dead beautiful thing I've seen in a long time. There's nothing symmetrical about it. So to claim that ideas about beauty are universal just doesn't work. So I think math is beautiful, but it's certain aspects of it maybe not necessarily beautiful to other people. That said, there are lots of aspects of mathematics that are about non-symmetry and chaoticness, which are also beautiful, but in a very different way.
Well, and there's also a bit of a backlash here. I mean, for instance, there's a new book by Sabine Hosenfelder, Lost in Math, arguing that physics is actually stuck because it's so hung up on beauty, so hung up on, looking for these elegant formulas that maybe that's held the whole field back. Jim, I mean, you've made your name through supersymmetry, so I'm guessing you have some thoughts here.
So I have some opinions. Let me start, however, with a quote. It won't be precise, from Albert Einstein. And he has this interesting quote that mathematics and science, when practiced at their highest levels, coalesce in aesthetics, plasticity, and form. So the kind of beauty that people like me find in mathematics, there's a story I like to tell people to try to pass along an understanding of what we're dealing with. And it goes as follows. Imagine a planet on which there's no sound at all. But there are beings of our ability that occupy this planet. And you can imagine a small group of them learning how to score music. Because after all, on our planet, we not only listen to music, we have musical scores. And so on this planet, let's imagine that's the only way that music exists. Then for those special, they might have a name, musicians, who study these arcane figures on paper. But on our planet, we also know that people who score music will tell you that they can, in their mind's ear, hear the composition. So what would forbid these aliens who know how to score from experiencing that way to access music? So that small group would talk about the beauty of this symbolic representation system because they're experiencing it the way that humans experience it who both score and hear it in their mind's ear. That's kind of what happens to those of us who engage in mathematics, is that we're by training, accident, genetics, whatever the circumstances are, there's a notion of beauty that comes through these symbols. And I have some suspicions. I would disagree a little bit, but I have
good. I'm glad you're going to disagree a little bit.
But I have some suspicions that part of what humans find beautiful is a reflection of the way that the circuitry up here works. That if you actually study the patterns of electrical flow through brains, that it's likely, and I believe, that somehow that's what we're reflecting when we talk about a beautiful song or a beautiful picture, that it's some echo or remnants of that. So it may not be universal, but I think it is, in fact, grounded in a much deeper way than you might think is a cultural definition of beauty.
I'm so thrilled that you brought up this planet of aliens who can't hear but can only relate to music as a score, Jim, because I've actually been writing about this issue, but I haven't heard about the planet of the aliens. What I've been interested in is that I think you're right, that music is a fantastic parallel for thinking about mathematics and mathematics in the world, because if you think about music, you can write down music and score it and learn it through that methodology and play it through that methodology. But most musicians throughout history did not write down scores, and there have been plenty of great musicians who didn't read music, people like Jimi Hendrix, and apparently Michael Jackson said he didn't read music. So there are plenty of great musicians, even people who play very complicated music like jazz, who don't read music, but yet they do it. and I want to make this claim about mathematics, that you can learn mathematics symbolically like you and I did at university by studying equations and textbooks, but you can also learn a lot of mathematics by doing it, by learning it through playful materialized concepts and practices, and that's what I try to do with my art and math projects. But this actually has really wider philosophical consequences, because it goes like this. I believe that what this means is that when we find mathematics incarnated in the material world, in things like organisms, like say coral reefs, which the coral organisms embody non-Euclidean hyperbolic geometry, I want to make the claim that the corals and the sea slugs actually are doing non-Euclidean geometry, and that constitutes a form of knowing. So I want to ask the question, does a sea slug or a coral, which are completely non-conscious beings, do they know hyperbolic geometry? And I want to say, yes, they do. It's an incarnated form of knowledge, but it's to me similar to music. Jimi Hendrix couldn't read music, but no one would say he wasn't doing it.
But this also has an interesting implication. So how is it that our species has been enjoying all of this interaction with music for perhaps hundreds of thousands, maybe close to 1 million years? Mm-hmm. It's because there have been instrumentalities, whether it be the voice or flute or drum. There have been objects and parts of our body that we have used to generate music. So if you start to think about mathematics, although you talked about the example of sea slugs, I often like to say dogs were the first one to learn how to learn Newton's second law. Why?
Because they can catch.
Because they can catch, exactly. No, but seriously, you go to the park and there are lots of smart dogs out there, right? Their owners are tossing sticks and balls and they're catching. So at some level, that's the doing of mathematics. You don't have to go to sea slugs. However, something new has been added to the human experience. It's called a computer. And I like to think of a computer as an instrument on which math is played. And if that analogy holds, I would posit that in the future, the interactions between humans and mathematics, mediated by computers, will come to resemble something far closer to the interaction between humans and music, but now computers playing the role of instruments.
But now there's a huge argument going on about computers in math, because there's this, we've got all this ability now to have software programs that can be set to, can you prove a theorem with software? And when I first heard about this, I thought, oh, wow, that's really cool. But I talked to my mathematician friends, and a lot of them were horrified. And they don't a lot of mathematicians still won't accept mathematical proofs. And they think that, okay, you can prove with a computation that the theorem is true. But a lot of mathematicians won't accept that it's a real proof until you've actually hand done it. And I think that's really lovely.
I want to follow up on this idea of sort of this close correlation between math and music. And this goes back, of course, millennia to the idea, the notion of the music of the spheres. And I'm wondering if that was just an interesting metaphor or if it was more than that. And of course, there's a whole sort of spiritual history as well. I mean, people saw these numbers as sort of a way to, I believe, sort of connect with the divine, right?
Well, certainly the Pythagoreans thought that. The Pythagoreans, most of us in the modern world, of course, we know about Pythagoras' theorem. It's something that we get tortured in school with for a few years and then we forget about it. But the Pythagoreans in ancient Greek, although they were fascinated by numbers and such relationships, they thought of these as religious activities, not divorced from their spiritual nature, that it was part of a spiritual setting. So the whole question of how one pulls numbers out or in a particular neurological or sociological setting will obviously vary from society to society. I think those of us who are scientists are kind of stuck in a rut. And I also think that mathematicians are stuck in a rut, because I think that computers are going to powerfully impact the way humans interact with mathematics in the future. And this whole issue of a proof, I agree with you because this is something I confront in my work rather continuously these days. I like to tell young people, A, you need to learn how to code if you're going to do theoretical physics, which is a kind of a radical statement. I mean, after all, why do we need to learn how to calculate anything accurately, right? But the point is that you get all this mathematical power. It's like putting on the Iron Man suit, and suddenly you have, in the mathematical world, we have this enormous power to grasp and see more mathematics and to look at more of these forms that my colleague is talking about, and these patterns. Suddenly it's like putting on a pair of glasses. And I think that somehow, when enough humans experience that, this symbolic way that you and I learned it, it may in fact become very much like asking the question of why was Jimi Hendrix such a great musician, but he couldn't read music? It may, something like that may occur in math.
What you mean that the computer could be, as it were,
The instrument.
Yes.
The instrument.
But it's interesting that a lot of mathematicians are resistant to this idea. Why do you think that is, Jim? Why are they so affronted by computer proofs? And I mean, to me, there's a lovely aspect of their insistence that a real proof is one that's literally hand done.
Sure.
But why do you think this? Why do you find your colleagues so resistant to this idea?
I think it has something to do with a point we touched on earlier about creativity. Let me relay a story. Some years ago, I was in a meeting with Eric Schmidt, and he looked over at me and he said, Jim, in maybe 20 years or so, Google will be able to have artificial intelligence that do what you do. And my response was, not unless the artificial intelligence can dream. Because the
Do androids dream of electric sheep?
Do androids dream of electric sheep? A question that has been asked in science fiction for several decades, right? Those of us who are fans know about such things. But I think that part of the resistance that I see it in my mathematician colleagues also, part of the resistance is that the computation may have an exception in it that they're afraid that somehow can be missed. But of course, that's true.
That's true of
That's
human
true. That's right.
proofs,
That's
too.
true anyway, because that
Yeah,
we
right.
were earlier talking. You were talking about non-Euclidean geometry.
But explain this. So why do you need that capacity to dream, that to tap into your unconscious to be able to do what you do?
Well, the way I understand it is related to. So I have in physics what I call my hero Maximus. His name is Albert Einstein. And once he made this very interesting statement that puzzled me for decades. The statement was, imagination is more important than knowledge. And for me, this was a puzzlement. It was a source of puzzlement because imagination meant for me reading comic books, going to the movies and watching space adventures, perhaps some stories about magic and what have that. To me, that was the use of the imagination, or painting or drawing. Knowledge was how we got to the moon. And I was born in 1950, so I watched the space age, the race to the moon. So how could it be that this frivolous activity was more important than the technology that ultimately provides a level of comfort for our species that's greater than has ever existed in our history? How could the play be more important? And after several decades, and I literally mean decades of thinking about this, I came to the following conclusion, that knowledge is like a finite ball, and it has an edge beyond which we don't know the answers. So this is true now. Come back and say 15 years from now, that ball will be bigger. How did it get there? How do you get this new, larger ball? And the only thing that I've concluded is, right at the edge where you're trying to get it to grow, we make up answers. We literally make up answers, and that is part of the creative process, just like writing a story.
And you're saying computers will never be able to do that?
I have difficulty understanding how they're going to be able to do it. But if Eric was right, then I'm replaceable.
Do you know how that's just, I love your story about the ball getting bigger, Jim. You know Einstein's famous quote, imagination is more important than knowledge. Most people don't know how it goes on. So it goes, imagination is more important than knowledge. Knowledge is finite. Imagination encircles the world. which is
So it's imagination that's driving the
insert.
growth of that ball,
Yeah.
which supports our increased technology. That's why he got it right.
yeah.
So I want to pick up on some of the threads that we've been talking about, going back to, for instance, Pythagoras, and this sense that there was profound meaning that was embedded in the world of numbers, and I'm wondering what if that resonates at all for you in your own life. I mean, if you actually find some sort of spiritual sustenance in the world of mathematics, in the world of numbers.
Well, my first book is called Pythagoras' Trousers, and it's a cultural history of the idea that math is a spiritual activity. And Pythagoras' idea that the music of the spheres, which you talked about earlier, was very specific because it did relate to music. So Pythagoras discovered his famous Pythagoras theorem that, as Jim said, we're all tortured with. But more importantly, he's the person who discovered that there are mathematical ratios between the lengths of the strings on a lyre. So if you have a lyre and two notes are an octave apart, they will be in the one of the strings will be twice as long as the other, and all the musical relationships, the third, the fifth, etc., have these whole number ratios between them. And so there's a reason why it's called the music of the spheres, because he thought of music and the ratios embedded in the strings of a lyre as actually being a model for how we could think of the structure of the cosmos, that he thought that all of the distances from the Earth to the planets and the stars were also a set of ratios, and this was the divine music encapsulated in the great cosmic lyre. And for Pythagoras, this was, he actually literally thought that the numbers were gods. So for him to study mathematics was actually to be studying the doings of the gods, the Greek gods. And this idea got incorporated into Christianity in the Middle Ages, when Pythagorean Greek philosophy, and particularly Pythagorean philosophy, also came into Christian culture, and it got reconceived of the idea that God had created the world according to a set of mathematical relationships. So God was the great geometer, God was the great mathematician. And so the fact that you've got people like Stephen Hawking, etc., now talking about the mind of God, goes back 2,500 years. That's an indisputable part of Western history, and therefore it's an indisputable part of the history of the way science did evolve, because people like Newton and Kepler and Copernicus and Galileo all believed this. They were Christians who were trying to articulate the work of God, the Creator, as a mathematician. But it didn't have to be like that. Math could have evolved, and mathematical science could have evolved in a non-theological context. And much as I'm deeply interested in the history of this intersection, I personally don't think that math is divine activity. It's divine in the beautiful sense, in the mystical sense, but I don't think it's divine in any theological sense. And I actually strongly object to this, as it were, use of God as a PR mascot for physics. I think it's really, really problematic.
And I'm going to make a comment about Pythagoras. Pythagoras, in fact, did not discover the Pythagorean theorem. It was known at least a thousand years before he lived. However, he's the first person that we know constructed a proof of the Pythagorean theorem, which, interestingly enough, touches on 2 points. Earlier you talked about how you experienced pi as an entity that entered your life, shall we say. Pythagorean theorem, since it was over 1,000 years old by the time that Pythagoras lived, meant that some set of individuals must have experienced the theorem as something that they encountered. And what the most likely situation is people involved in some sort of construction, that they were out perhaps doing figures in the sand and drawing triangles. And you can imagine that that's how just as pi came into your life, that for our species, that's how the Pythagorean theorem came to us, is that there were people doing something. And this also illustrates something I think that's very powerful. First, in the message that Margaret had about the engagement of a human mind with an activity that lets you discover mathematical structure is something that we as a species have benefited from, and that we need to celebrate and provide opportunities for people in our education system. We talked about teachers earlier tonight, and I'm involved in some policy discussions around STEM ed, but it's a modern rediscovery that if you want to teach people mathematics, you give them an opportunity to experience mathematics. It becomes a much more powerful tool.
And actually, on that, I'm glad you raised that point, Jim, because today is the 10th of the 10th of the 2018, and it happens to be the day that it's called Global Math Day, and there's an amazing project going on this week called Global Math Week, started by this wonderful mathematician, James Tanton. And they are getting, last year they had 1 million kids involved, and this year they're hoping to get 10 million kids involved all over the world. And it's exactly doing what you're talking about. He has this amazing methodology he calls exploding dots, where kids, it's not just for kids, it's for adults too. You draw these dots on paper and you can perform not just basic arithmetic, but actually really high-level algebra. And it's this incredibly experiential, graphical, and really joyful way of teaching math. And it happens to be, this is its big day.
Humans, I believe, are actually intrinsically mathematical. In the
Yes,
same way
I think
that,
so.
in the same way that, you can watch small children draw. And here I'll relate a personal family story. My son started spontaneously adding at 2.5 years old. And it wasn't anything sort of that we had taught them to do. It was just sort of they hung around. And he was actually playing with ducks in a tub at the time. And he demonstrated me that, you take 2 ducks and throw them in the tub, and you have 2 ducks. And you take 2 more ducks and put them in front of Dad's face. Say, 2 ducks. And Dad says, yes, 2 ducks. And he throws those 2. And then he says, 4 all ducks. So it's clear that addition is going on here. But the point of the message is that we as a civilization, in my opinion, do not celebrate that kind of activity in young people. Even before they get to school, you can do this very simple thing. We actually threw him a party. Like a birthday. We actually threw him a party. And every time one of my twins mastered one of the basic arithmetic operations, we threw them a party. And it was my daughter who mastered the hardest of all, division, and she got the biggest party.
So we've been talking about the power of mathematics, and partly as an explanatory tool for how the universe is structured. I'm also wondering about the limits of mathematics, and let's talk about physics for a moment here, because string theory is based on mathematics. The whole idea of the multiverse, that we live in one of many universes, that is grounded in mathematics. But as far as I know, there's no empirical proof for any of this stuff. And yet theoretical physicists have been running down this road for years, for decades now. And there are real questions. Are physicists too hung up on math? I mean, maybe we need to go back and sort of look at more empirical proofs to try to actually figure out how the world works.
Well, although I'm often referred to as a string theorist, I never refer to myself as a string theorist. I am a physicist who works on this subject called supersymmetry, which is part of string theory. It's at the foundation of string theory, and that's really where I've spent my entire professional life. And yes, I have watched my community as we look for ever increasingly sophisticated and to us beautiful mathematics to guide us along the path of greater understanding of nature. But we also, some of us at least, also believe that the final arbiter is nature herself. So although there are the kinds of criticisms that people make about, they're lost, or it's not even wrong, which is another expression that one encounters, as a conservative physicist, my comment is, so far, this idea of beauty and symmetry, which Steven Weinberg expressed even in Newton's work as combining the celestial with the terrestrial, this idea, in fact, has driven our science for several hundred years, and if someone has something better, let's see the results.
So this is interesting. So you'd call yourself a conservative physicist, but you also work in string theory. Okay, you don't call yourself. So that's conservative physics now, is to accept string theory.
I am not a religious fanatic about string theory.
This question about the limits of math. So physics is actually what distinguishes physics as a science, and the way that it was historically invented is to be the science that finds mathematical relationships in the world. So, Sabine Hosenfelder's new book, Lost in Math, it's not that she's saying we can get beyond math, because it wouldn't be physics if it wasn't looking for math. It might be something else, it might be biology or chemistry, but which are no less legitimate and no less true. But physics as a science is the science whose goal is to find the mathematical relationships in nature. Sabine's argument is that some physicists have become too invested in particular kinds of math. So one of the things that one finds in the history of physics is this incredibly beautiful interplay between discoveries in nature and discoveries in mathematics. And sometimes discovering new kinds of math enables you to discover new things in the material world, and sometimes discovering new things in the material world leads you to discover new kinds of math. And one of the things that has been pretty astounding in the history of physics is there's so many examples where mathematicians have discovered come to some amazing mathematical discovery, and you think, or mathematical insight, and you think that's so bizarre, it could never possibly be realized in the world, and lo and behold, it is. But is there a limit to how much mathematics could be incarnated? We don't know. Is there a limit to how much incarnation can be described by mathematics? And I would argue that yes, there is. I mean, I think that an enormous amount of things in the material world have got some kinds of mathematical description, but I don't think that math can ever be the totality of our description of nature. Just take something simple like smell. We might be able to have mathematical computational models of smell, but that's not actually smell. It comes down to the thing, I suppose it's like the consciousness issue about the hard problem. Do you think there is actually qualia, an experience? And I'm one of those people who believes that there is, and that stuff is not necessarily reducible, transformable into mathematical language.
Well, let me follow up on that, because, I mean, we've been talking, the premise of this evening, of this discussion to some degree, is that mathematical laws are primal in terms of how the universe is structured. There are other people, famously William James, 100 years ago, the philosopher, who said that consciousness is the only thing that's real. Where does consciousness fit with mathematics?
That's a hard question, Jim. I'm going to let you answer that first.
And you will note that I was sitting here quietly and peacefully as you were about to answer. Where does consciousness fit in? Well, as I said, for me, as I've experienced my life, there are kind of two parts of it. There's the rationality, and that's the part that at some level is it's the part that connects the mathematics and the patterns that I see in nature to mathematics. It's that questing part of my mind that has a need for looking for order, because somehow it feels better. And I'm just going to put it in those terms. It just feels better to know what the orderly rules are. On the other hand, there's this wild west part of my mind. I keep coming back to the subconscious or unconscious. And what drives it, I don't know. I know that it's probably where my dreams are coming from. I'm pretty sure about that. So when I get an inspiration or a deep insight into something that I maybe didn't think I could ever answer, it seems like that's the part of my mind that's doing that. But whether consciousness itself is reality, I beg to differ. That's for me a bridge too far. I don't think that. Well, let me say it this way. Often I talk to people who are not scientists, and they will ask questions like, "Well, what is time if we don't exist? I mean, suppose there were no conscious beings on the planet, then how would you know that time passed?" And my answer is, well, there are actually geological processes such as tree rings, very similar tree rings, that record the passage of time. So time doesn't need a conscious mind to exist. We can find evidence in the natural world around us. So this idea about the primacy of consciousness is not one that I can ascribe to as a scientist, as I have observed the world for almost 70 years now.
Well, I think you just said something that I think is critical. You said if there was no one around to know about time, would time still be passing? Well, to a certain degree, it's a tautological question, because if there was no one around to know it, what would be... There's no one to, as it were, speculate whether time's passing or not. The world is there existing, but there's nobody to be debating whether time is real or not. And so it seems to me that one of the things that's critical to comprehend about physics is that physics is a science invented by rational conscious minds to describe to themselves the order they see around them. Now, the order exists in the world whether we describe it to ourselves or to anybody else. But the project of physics is to describe that order to ourselves and to other conscious beings. So I would say, what does it mean to say that those mathematical laws exist in the absence of conscious beings? Because I would argue that the mathematical description is only there in as much as we use it. That doesn't mean the order isn't there, it's just there's no description of it. So the order of the world is a separate thing than the mathematical descriptions of that. And this is what Brian Rotman's trying to get at in what I think is the great book about the philosophy of mathematics.
And I would agree with that statement. I earlier talked about the fact that we can't
You did,
free,
yes,
we cannot
absolutely,
free ourselves from this irrational part that is part of the calculation. Why do we care even about the order? There are deep emotional issues that drive this. So the existence of math to me is tied up with the fact that there are beings who are doing the observing, but that doesn't...
Brian Rotman couldn't have said it better.
So we talked earlier about computers, and
Yes.
I want to sort of bring computers back into our discussion, because there have been various models about how the cosmos is structured, over the centuries. And, at one point, people talked about the clockwork universe that we lived in. And now the computer is often the metaphor for how the universe is structured. And Jim, I know you've done some work on this whole idea of maybe we should take that idea more seriously.
No, we shouldn't. But you forced me to a point where I have to speak. So I don't know how familiar the audience is with some of my research, but leading a group of both mathematicians and physicists about 10 years ago, we found an extraordinary result in some of the equations that are part of string theory. As I said, what I really do is I work on a subject called supersymmetry. So it's got symmetry in it, but it's got more symmetry than you probably should want to ever see. In the mathematical context of such equations, we have discovered that there are mathematical structures that are indistinguishable from error-correcting codes, as does occur in digital information transmission and establishing reliable digital information transmission. And because of this, many people have concluded that the work that I and my team completed means that the universe in which we live must resemble the science fiction movie The Matrix, where we're all some kind of simulation of some program running, and that's exciting for a lot of people.
It's a little unnerving.
Well, and then there, of course, you have Bostrom, Nick Bostrom, a philosopher, who has really, put this point front and center for the public and for.
Who says the computers will take over?
Yeah. It basically says that we're all just simulations. I like to point out to people a couple of things with that that I find problematic with that. One is if you accept that, then you have to also accept the existence of ghost.
Existence of
ghost. Edgar Allan Poe. Ghost.
Oh, okay.
Ghost. Right?
Why, Jim?
Because if we are simulations, there's some kind of substructure that we don't have access to that runs us as an app. So when we die, what does that mean? It means that that particular app was ended. That the app stopped running. Right? But if that underlying superstructure still exists, and if there's no damage to the codeware, whoever is running this superstructure can re-enable a app, let's say Jim Gates 500 years from now. So Jim Gates comes back as a ghost. It's built into the idea that the universe is a simulation. This doesn't sound like the universe I exist in. So although many people like to say my work supports simulation theory, I actually believe that it's pointing to something far more beautiful and subtle about the nature of the laws of physics.
So I want to go to the audience with their questions in a little bit, but Margaret, there is a very interesting red object sitting on the table next to you, a piece of crochet. Can you explain what that is?
Thank you, Steve.
And you can hold it up to the audience so that we can see this.
So I said earlier that sea slugs and corals and lots of organisms in coral reefs embody a kind of geometry called hyperbolic geometry, which is an alternative to the Euclidean geometry we learn about at school. And mathematicians discovered this hyperbolic geometry in the early 19th century, but it was only after hundreds of years of trying to prove that anything like that really wasn't possible. And the discovery of hyperbolic geometry ushered in the whole field of non-Euclidean geometry, which is now the geometry that underlies general relativity and will tell us about the structure of the universe. So what's really two things that are fascinating to me about this. One is that while some of the greatest mathematical minds were trying to prove that this was impossible, brainless sea slugs and corals were meanwhile just getting onto it because they'd never heard about Euclid's laws and they didn't know it was impossible. But so mathematicians discovered that hyperbolic geometry was possible, and it's like a geometric equivalent of the negative numbers. They discovered that at the beginning of the 19th century, but they didn't have ways to make models of it. And it wasn't until a mathematician at Cornell University, Dr. Dinah Taymina, came along in 1993, and she said, you know what, guys, I think I can make a model of that with knitting and crochet. And so she did make a model of it, and this is one that she made, and she showed that you could stitch lines onto it to demonstrate the underlying mathematical insight about this space, which is that it doesn't actually conform to one of the postulates of Euclid's geometry, which is called the parallel postulate. So here in crochet is a stitchery woolen proof that the most famous proposition in mathematics isn't actually true. And what I like about this is this issue that mathematics actually is something that can and often is incarnated. It isn't just this abstract thing. It is actually there in things, and that by actually manipulating things and building things and making things and doing things and playing with things, we can actually play mathematics.
Okay. If your mind has not been expanded after this discussion, there's something wrong with you here. So raise your hands if you have questions, and we're going to kind of swivel around here so we can see the audience. So there are a couple of roving mics here, and you cannot talk until you get a mic. But let's go to the woman right at the front here.
I have a very simplistic question. I was wondering, you had mentioned the difference between a physicist and a mathematician, and there are no mathematicians here. Is that because they really don't care how their work relates in the real world?
So I'm not sure what's the question. Can you?
Well, you're both in physics, but physicists, right?
Actually, well, Margaret, you should explain your background.
Oh, well, I'm not a practicing physicist. I studied physics and math at university, but I'm a science writer. So I'm not actually a practicing physicist or mathematician.
Right, but there are no mathematicians.
Well, that's because there's only two people. So I'm
So,
sure
I mean,
there would have been many
what-
mathematicians who they could have invited.
What's the implication of
The
your question? here?
implication, as you're saying, physics relates mathematics to the physical world. So are mathematicians really the creatives that they do their work without concern if it relates to the physical world?
Oh, absolutely. The answer to that since about 1850 has been yes. So up until about the 1850s, there was this, most people historically had been physicists and mathematicians, and it was most, up until about the 1850s, I think most mathematicians believed that all mathematics was incarnated in the world. But in the 1850s, a fundamental shift happened that really is the development of modern mathematics, where mathematicians started to discover all these, seemingly bizarre, impossible things like Mobius strips and Klein bottles. And a great mathematician called Augustus de Morgan wrote a book, I think it's in 1860, where he actually spelled out the new philosophy. And he actually says in this book, from now on, mathematics doesn't have to relate to anything other than itself. Mathematics can be applied by physicists, but as mathematics, it doesn't have to be about anything. But that was a fundamentally new attitude to mathematics.
But one of the weird things is that physicists keep creating mathematics that mathematicians don't.
Yes.
And there's a series of examples that you can see.
Mm-hmm.
One of them is something called the Dirac delta function, which was created by the physicist Dirac in the 1930s, and it led to a whole new form of mathematics called distributions that came out of it. The invention of quantum mechanics, I don't know if it created the whole notion of Hilbert spaces, but it certainly blew up the notion of Hilbert spaces in mathematics. So even though physicists aren't mathematicians, we often, because we're wrestling with ideas of how to describe nature, we come up with mathematical constructs that do not appear previously in the mathematical literature.
Okay, let's go to John up front here.
This is really an amazing conversation. Thank you so much. So my question has to do with how hard math is and whether or not it's becoming too difficult for normal people and even for people who are mathematically inclined. So I'm a science writer. I actually reported on the solution to Fermat's last theorem 25 years or so ago. And as I recall, originally the problem was that there are only a handful of people in the world qualified to say whether the theorem was true or not. And it took a long time for people to decide, yes, it was true. I have heard mathematicians say that it's getting more and more, it takes more and more time to get to the frontier of a mathematical field. Nobody can understand the whole mathematical landscape anymore, and this is one reason why computers are being used. So I just wonder if you can comment on this trend.
Yeah, this is a great question, John, because there's a wonderful case of this going on right now. There are two very prominent mathematicians who both of whom have solved major problems before in mathematics, who claim that they've got proofs of what's called the Riemann hypothesis, one of the most famous and difficult propositions in mathematics. And the proofs are 1,000 pages long. And one of the problems is that nobody else wants to spend 3 years of their life working through the proof, because there may be a fault on page 935 and you've lost 3 years of your life checking somebody else's work. So it is becoming a problem, and as you say, this is one of the motivations for doing it with computers. And it's it is a pretty difficult problem to get around, because math, it's so vast, it's so successful, there's so much of it, and nobody can know anything like the totality of it anymore.
And the only comment that I would add is, first of all, I would amplify and associate myself with every single point that was made. And the other thing is, I remember some years ago trying to estimate how big mathematics was in comparison to physics. And the minimum estimate I came is that it's at least 100,000 times bigger as an intellectual space, mathematics is compared to physics.
Wow. Wait,
At a minimum.
explain that. What do you mean by that?
Well, what one could imagine doing is setting up some kind of measure of sort of ideas. Now, I didn't rigorously go through that, but in some hand-waving fashion I tried. And so I tried to figure out what is the sort of the galaxy of ideas that I see that drives physics for the last several hundred years. And then the decoupling that we talked about, which was around Riemann, and there were a group of four physicists, Gauss, Boyer, Lobachevsky, and Riemann, who brought this new idea into into mathematics, which is in fact the freeing of mathematics from physicality, because it says you no longer need physical instantiations of mathematics, that you could think of mathematics in a really abstract way. So once you understand that liberation took place, that means that for almost 200 years now, you've had the freedom to create a set of ideas that are totally disconnected to describing reality. And then you can make an estimate about how many new results in that time to evolve. And I came to the conclusion it was at least 100,000 times 100,000 bigger and growing.
So what you're saying is, Jim, is that basically of all the mathematics that we know about that we can actually affiliate with a physical thing, there's 100,000 times as much
100,000 times 100,000.
Well,
at a minimum.
Because, Descartes asked the question, is all of mathematics realized in the physical world? And his answer was yes.
But I don't think that's right.
But I sometimes wonder how many mathematicians would actually agree with that now. Not very many, I suspect.
Okay, let's go to back there.
Hello, and thank you guys very much. Appreciate how you guys conveyed your points. My question is, the numerical system that we primarily use, the 10-base numerical system, is that an arbitrary system? And if so, how does the mathematical universe explain for that?
Do you want to answer that?
I can try. It's terribly artificial, and it seems to have something to do with the fact that we have 10 digits. No, literally.
Yeah,
But it's been very useful, right?
Well, yes.
But to elaborate a little bit, we use the 10-digit system, and that's called arithmetic. But as mathematicians like to say, most mathematics has nothing to do with arithmetic. Most mathematics is involved with entities, objects, whatever word you want to use, that are not what most people would think of as numbers. So here's just a very simple thing. You know, one important object in mathematics is matrices. You know, I hope kids learn, I hope you all know what a matrix is, but, you know, it's like an array of numbers, like you see a grid of numbers. So, you know, matrices form a pretty big sub part of mathematics. And, you know, matrices can be 2 by 2 or 3 by 3 or 4 by 4 or, you know, 900 by 900 by 900 by 900. They can be in any dimensions. They don't have to be square. So most of mathematics isn't about bases of any kind whatsoever.
There's a very famous joke about mathematicians that illustrates their relationship to numbers and counting. So there are two mathematicians, and one is a friend to the other, and one of the mathematicians says to the other, there are actually three kinds of mathematicians: those who can count and those who can't.
But there's a very sweet story about this. So, you know, when everybody here's probably read Alice in Wonderland, and the famous line from the Red Queen about believing 6 impossible things before breakfast. Well, Lewis Carroll, Charles Dodgson, was a practicing mathematician, and he was involved with the development of what's called modern logic, which is the part of mathematics that helped to bring into being this new idea that mathematics isn't about anything other than itself. And that line about believing 6 impossible things before breakfast was precisely to basically, that was Lewis Carroll's comment on the fact is that's what mathematicians were doing. They were believing 6 impossible things before breakfast, like a Klein bottle, like a Mobius strip, like a matrix. And there's a lovely story that so Alice in Wonderland did really, really well, and Queen Victoria was so enchanted with it that she wrote to Charles Dodgson and said, you know, when you publish your next book, would you dedicate it to me? And he happened to be a mathematician who was also involved in developing the mathematics of matrices. So he duly sent her his next paper on matrices and dedicated it to her.
Okay, more questions from the audience here. Let's go over here. Yes.
Yeah, hello. There are many thousands of mathematicians in the world, each year turning out many thousands of theorems. So in 100 years, there'll be millions and millions of new theorems. Do we need all that?
There are many, many thousands of art galleries and artists churning out millions of works of art. Do we need that? I would argue that, you know, art has a fantastically significant role in our lives, and so does mathematics, and it doesn't all have to be useful.
And there was another question right behind the gentleman.
Hi, thanks for a great discussion. I wondered if you could talk about how some of these ideas relate to quantum physics, and specifically some of the recent work in emergent space-time and, you know, ADS-CFG correspondence, and how everything can be described in lower dimensions.
Is that all?
Do we have another 5 hours?
Do we have another 5 years?
Well, yeah, in a short time, I know of no simple way to explain those kinds of ideas. They're right on the cutting edge of what my community is producing now, and they're very exciting to many people.
Do all of these principles that we've been talking about, I mean, I don't know if our discussion has mostly been focused on classical physics, or, I mean, do the rules change once you get to quantum physics?
So, again, I'll tell you a story. So I did my undergraduate work at MIT, and I remember in my second year there, experienced something very interesting. At MIT, the first, like most physics classes, you first learn about the physics of Newton. And then you learn about the physics of Maxwell. So you then know how balls and billiard balls bounce off of each other, and then you also know about how charges and magnets work. And then there's a course on waves, so you can talk about water waves, light waves, what have you. But the fourth course is actually quantum mechanics. And I remember taking the course and and so this is with a group of people that I've now in course number 4. And many of my classmates were emotionally upset about quantum mechanics And the reason was because it had no apparent relationship to their intuitive understanding of nature that they've gathered over 20 some odd years in life. I had none of that. And I realized that the reason was because I understood when I was studying Newton's second law that that was not reality either. And so the fact that I simply shifted between a set of rules which apparently are accurate within their domain, that did not cause me any great disturbance that now I had to use a different set of rules to talk about electrons. So yes, quantum mechanics is very different, but it's math. And that's the thing to keep in mind.
One last question. Let's go to the gentleman in the middle there.
Really enjoyed your conversation. I did a thesis on non-Euclidean geometry of relativity, and this led to something that I found, for example, that the relationships between speed, energy, momentum could be related to a catenary, and that this relates relative to reality, that the idea of fractals, that the universe is self-similar in many different ways and levels. I think you mentioned something you mentioned about that, the idea of basically you see a similar relationship on many different levels and in many different contexts, like the catenary and relativity relationships. I don't know if you have any comment on that.
Well, I think this idea of self-similarity and fractals is an idea that began to emerge in Western mathematics about the end of the 19th century and really burst into sort of our consciousness maybe in the late 70s, early 80s, when computers were powerful enough to start making drawings of fractals, because you have to do a lot of iterations of things to actually see the structures. And it was an incredibly important development in modern science and in modern physics, because it hadn't beforehand being realized in classical physics that such structures, which are iterative structures, they're algorithmic rather than analytic, which means that you produce them by doing a little recipe saying, like, do this little sequence of things and do it 1,000 million times. So that's an algorithm to produce these structures rather than an equation, which is what we call analytic. But one of the things that's really interesting about this is that, so the discovery of fractals and self-similarity and mathematical description of it has really become an incredibly important and powerful tool in contemporary science, not just physics, lots of sciences. But here's a beautiful thing. We now know that African cultures discovered fractals at least 1,000 years ago. So there are lots of designs in African textiles, in African sculpture, in the way people braid their hair, and even in the architectural design, the floor plan of African villages that are fractals. So they were not, as it were, writing down the mathematical algorithms, but they had understood the concept at least 1,000 years before Western mathematicians.
Well, I keep learning new things throughout this conversation. I want to thank you all for being an amazing audience, and special thanks to our guests. And a couple of final announcements. We have 2 more events coming up in our series. Our next panel is December 6th. Human Cognition and the AI Revolution. And our final event is February 7th, Reality is Not as It Seems. Tickets are still available for both. And in case you didn't know, there is now a reception, and you can continue the conversation. Thank you very much.